About again a barrier issue. We had several of those, in this case alveolar barrier and involving particles in the lung. Go ahead, please.
Okay. Good afternoon, or Moyen, as we would say in Luxembourg. And as you probably can hear from my accent, it's not Luxembourgish, it's Austrian. We two come from the same country. What I will present today to you is a model we developed in Luxembourg, and I will not show you any data related to nanoparticles yet, but I will show you the model as we have it today, what we think is very functional, and now we are going to start to use it for particulate matter and nanomaterials. And I do not repeat anything on nanoparticles and sizes, but I have one slide on the structure, the histology of the pulmonary system. And the deeper you go into the lungs, the thinner the walls become. In the bronchioli, you have a lot of different cell types. You have muscles, you have chondrocytes, you have a thick layer of surfactant, while in the alveoli at the end, you have only a few cell types. It's very thin. You have a thin layer of endothelial cell and coverage by surfactant, and that's mainly what you will find there. Yes, we were not the first one who did a multi-cell culture system based on pulmonary cells. The original one, and as far as I know, the oldest one published is the one from Alfaro Moreno in 2008. But you see a few specificities with the system. The endothelial cells are seated in the transwell on top of your cells that are supposed to be respiratory cells. So this creates two problems. How are you going to dose your nanoparticles or your particulate matter to your pulmonary cells? That's quite tricky in the system. And of course, it's a very unfunctional situation in relation to which cells is where in your system. So what the PhD student Sebastian did is, in the first attempt, he immediately saw this kind of disadvantage and he changed the system, seeding the endothelial cells in the sixth well and having the other cell types in the transwell. What we use is epithelial cell, the A549, that is quite well known. And then we have macrophages that we differentiate into phagocytosing macrophages. We have mast cells and we have the endothelial cells. This allows us to keep the cells at the air-liquid interface. That was very important for us because we do not want to have nanoparticles in whatever medium that we have to inject to a medium. We want to have it from the airstream, and how we expose I will show you in a minute. So that's a big advantage. But actually, there was still this problem that the endothelial cells are not in direct contact with the pulmonary cells. So we decided to further adapt the system, and that's how we use it today. You have the endothelial cells on the lower part of your transwell, and I will show you in a slide how you can see it on the lower part of the transwell. And we have the other cells on top, and we have this system where we can expose cells at the air-liquid interface to particulate matter or to nanoparticles. What was very important for us is that in the physiological situation you have surfactant, so we wanted to know whether our cells really produce surfactant. That was one of the aims in the first period, because we want to have a functional system that is as close to the real system as possible. We wanted to see whether our macrophages are really taking up particles. I will show you pictures on that. Mast cells, of course, are supposed to produce histamine. We wanted to know whether our mast cells in culture at the air-liquid interface also produce histamine. And then we want to, of course, to know whether the cells are still viable, etc. And I will show you for all of these some results. That's the system, how it looks like. As far as I know, there are two commercial systems on the market. We have the Vitrocell system. There's also a system from Germany, the Gutleb system that some of you may have. And then the Karlsruhe Institute of Technology has a variation of this one. There are two types of particle generators. One where you can the particle with a kind of brush system into the airstream, and there's a centrifuge that the bigger particles and agglomerates are centrifuged away, so that you really have only smaller particles, meaning smaller than 300 nanometer in your system. And we can have a system where you also can evaporate chemicals, if that is of interest. And then you have 3 chambers where you expose and 3 controls where you have only an airstream. Specificity of our system as we bought it is that we have quartz balances in the system, so we can follow the kinetic of the particle deposition in time with a resolution of 5 nanogram per square centimeter. Or as my chairman said, why didn't you call this a 4D system? Because actually this adds the 4th dimension to our system. We have the 3-dimensional and the time. Thanks. Copyright to him. Okay, the viability. If you have cells in the air-liquid interface, it's quite tricky. The first time we exposed them, after 5 minutes, we had a dead layer of dried cells. So you have to play around with humidifying the air, the amount of airstream, etc. The dotted line gives you the viability of submerged culture. And what you see is there's hardly any difference between the single cells or co-cultures or tetracultures compared to submerged condition. And on the left side you have the nebulizer, and on the right of the doubles you have the air-liquid incubator. This means both systems do not produce a difference when you use it to evaporate particles or chemicals. So from this we concluded, okay, our system is stable, survives the exposure period via the aerosol phase. Surfactant. We wanted to know, do our cells produce surfactant? This is an immune staining of surfactant protein A, B, and C. And you see A and B in green marked are highly expressed, while in C there are only a few tiny shades. But we definitely have surfactant protein A and C in our system. This is now a surface marker for differentiated macrophages, CD11B. You see the green surface are clearly marked. This is a staining in a monoculture. So we have differentiated macrophages. The same now in the monoculture, the picture for mast cells in green staining of histamine. So all the different compartments, the different cells we use in our system are doing what they are supposed to do. Do we have a confluent cell layer? The blue line here shows you on the side the membrane of the Transwell, and you see the 2 cell layers, the alveolar cells and the endothelial cells, forming a complete closed cell layer. We have tested this also, there is nothing going through. One specificity, what is also described in literature, if you have macrophages at the air-liquid interface, they tend to form these colonies. When you put the samples, for example, afterwards in the submerged conditions, these colonies would disappear. That's something what the macrophages obviously do when they are in culture at the air-liquid interface. What we also saw is here, this is a colony of the mast cells, and in green stained you have macrophages. So you see that the macrophages start to invade the other cell types. And now comes after one slide there comes the tricky part, and the boys from the technical support had to help me because there's a video embedded. What you see on this one is we wanted to know, do our macrophages really phagocytose if they get a particle? These are the white spots are agglomerations of nanoparticles that we got from Nanotest, the FP6 project that some of you may know from Maria Dusinska. And we evaporated it into the airstream, and we find the nanoparticles afterwards back in the macrophages as seen by the green staining of the cell membrane. Now it becomes tricky whether we get the video started or not. Yes, they managed. Excellent. This is now one macrophage in high resolution where you even see the localization of agglomerations of nanoparticles within one single macrophage in green. So our macrophages definitely do the trick. They are phagocytosing if they are offered particles. Do the cells have oxidative stress? Can we induce oxidative stress, and how do they react? And is there a difference between the single cell culture model and multi-cell culture models? Yes. First, what we did is we used the chemical compound AAPH instead of hydrogen peroxide to induce oxidative stress, and you see on the left the first four bars are the single cell cultures. What you see is that A549 are much more resistant towards oxidative stress than the other three cell types used in our system. But you see a clear difference between the co-culture system of the A549 and the endothelial cells and our tetraculture system. So depending on what kind of system you use, also you would get different results. And our conclusion is that this system, because it is closer to the anatomy and the physiology of the pulmonary system, the results will be also more reliant. Another specificity of the system, you have your cells at the air-liquid interface. What you see here is that if you have cells at the air-liquid interface, they have a higher oxidative stress than cells that are cultured at submerged condition. The left bar is always the submerged condition, and the right bar is at the air-liquid interface. These are the A549, the co-culture, and the tetraculture. And you see in all conditions there is a significant higher oxidative stress on the cells. It's not unexpected to see this, but we see what we are expected to see in our system. So now you get the real details on how to do it if you want to go home and do it. On Friday this week you can seed your endothelial cells and your A549 into the Transwell. The trick, is it coming? Yes. The trick to do it is you simply turn around the Transwell insert, you put the endothelial cell on top of it, you wait half an hour, you turn it and you seed your A549. It's so easy as that. You immediately have on Monday a perfect Confluent cell layer on both sides. So what you would do next is, on Monday you start to stimulate and differentiate your macrophages. You add the macrophages and the monocytes on Tuesday to your cell culture system, and you can expose on Wednesday with the aerosol producing equipment. That's how it looks like. As you can see, I have a boy as a PhD student because he chose Ferrari red, as he says, on the car. These are all the different parts of the equipment as we have it. It's a modular system, so if you are interested in this, you could build from the elements that the company offers your own kind of system with how many replicates you want, etc. With this I come already to the end. The project is a cooperation between us, the Centre de Recherche Publique Gabriel Lippmann in Luxembourg, and my team with the university in Trier, Germany, Professor Blömecke. And of course we have to thank the Luxembourgish Research Council for funding this PhD project. And with this I come to an end. Thanks.
Thank you very much. Questions for this talk, please? Yes.
I'm from the Institute for Work and Health in Switzerland. I was wondering, did you consider the surface chemistry of the particles, whether it's hydrophilic or hydrophobic? When the cells produce surfactant, for example, then how will these particles behave on the surface of these epithelial cells?
This is a very good question, and I have to answer in a way that we have not tested it yet. We are now in the phase, and the manuscript is currently The revised version is currently back to the journal. So we start now to work on that. And also to answer a question, in the moment, in the first step, we only work with 2 commercial diesel particles. We do not have yet nanoparticles identified that we want to use. But as you said, we will have to consider these factors when we start to use them.
Hi, I'm Halska from the Institute of Work and Health also.
Oh, yes, I see you.
And so you mentioned that the aerosol producing system you have centrifuges so it removes particles above 300.
Yes.
But I'm wondering also if you can characterize the nanoparticles before they hit the ALI. So do you know how many particles per droplet, for example, come out of the aerosol?
If it's a powder, let's say like this, the system as we have it in the moment does not have an exit to get particles into any particle in aerosol measurement equipment, but that could be easily adjusted. We had just had a discussion this morning about that, but we don't know. What we plan to do, and I didn't show it because it goes beyond the scope of this, we have in-house an equipment called nanosims. It's secondary ion mass spectrometry. What we can do is we can have the cells like we have them, we expose them for whatever time of period, we take the Transwell, we put it into an equipment that destroys the material but gives you for 5 isotopes a mapping. So you will see where you have carbon, this will show you where are your cells. You will use phosphor, it will show you where are your nuclei. And then you can choose the other 2 or 3 channels from the mass detectors that you have for your silver particle, for example. And then you would exactly see where the silver is and how big the particles are within the resolution of the equipment. That's what we plan to do.
Martin?
I'm Martin Clift, University of Freiburg, Switzerland. Thank you very much for an interesting talk. I have 2 questions. In your co-culture system, have you actually measured the surface lining layer, i.e. your surfactant layer, to make sure it's all there and it's consistent? And 2, if you're intending to use diesel exhaust particles, which are a known antigen, do you intend to use dendritic cells in your system at all?
Okay, first question. We have done a kind of surfactant staining in light microscopy, and then you see that your whole well is more or less covered by surfactant. And for the second one, no, we have not thought about it yet, but that could be a very interesting addition, yes. And maybe a good thing for a cooperation.
Further questions? Let me ask you a final question about the system. I have a background in allergy, so I'm of course thrilled to see mast cells included here. Why did you include mast cells?
We have the system now, and in this moment, this PhD student will deal with nanoparticles. But if anybody of you know Professor Blömecke, she comes from skin and lung sensitization, and the acronym of the project is also nonsense, nanoparticles and sensitization. So there is a deeper meaning that we have not fulfilled in the first project. But we plan 1st of April we have a new PhD student and we go in a slightly different direction.
All right. If there are no further questions, then I thank you very much again.
Thank you.
Thanks to all our speakers, to our discussion participants, to our audience, and to our excellent technical support. We are closing the session now and asking you to be back for the next session at 4 o'clock. And now we hope for coffee. Thank you.